Thank you, distinguished MC. And
Thank you.
I want to use this opportunity to thank our able chair, who has been consistently supporting this mission since the last 3 years when this program started. One of the things I see in leadership is have a visionary leader who is always there to listen to the team, and then we share ideas. Without wasting most of your time, I want to welcome all my distinguished discussant on this platform. It's my pleasure to have you here. Once again, my name is Dr. Ken Uwalaka. I work for Antam Producing. I don't even know, work in so many places around the world. So we have discussed much on measurement, and then the next thing is digitization. So I want to use this opportunity to sweep a little bit on the program, because we have one of our presenters who is in Dubai. Because of time constraint, we will allow him to go first. That's Mr. Sherry. So after that, we can have a presentation from this team. So I want you to relax. But one thing I always ask oftentimes is, how digitized is our digital system? Everybody talk about digitization. How many operators here will say he is 70% digitalized? I see at different interval, at different nodes, human interference in the so-called digital system. From where I've come from, where I've been in the Western world, if it is digitalized, it is digitalized. The only time you have interference in that system is only when there is abnormalities, and then the expert will come in and resolve it. But here we simply sell solution called digital solution. And along the line, you find out that just a couple of entire workflow is digitalized. And with that point where there's human interface will make a mess of the whole system. So I look forward in this discussion, both the presenters and the vendors that sell digital solution to think towards helping the country, the business of oil and gas in Nigeria, to be fully digitalized for those who have said they have digitalized it. And let's remove human interference, which we have heard in this discussion, that we have a lot of inconsistencies, inaccuracies, variance in allocation factors, and so on and so forth. Believe me, 70% of it is caused as a result of human interference. So on that note, I want to thank you very much for being here. And if our first presenter, Mr. Sherry from Dubai, is online, can we have his presentation, Secretariat? Thank you. It's not ready? Okay, because of time, I would like to have Snyder to go first, or the lead speaker who is ready. Snyder is ready, so, but you're not the lead speaker, right? All due respect. You can go and make your presentation. So one more thing, I will plead with us that we put our questions together while this presentation is going on, so that we'll take all the questions at the end. Because of time, a lot of people may be driving out of this hotel or to another hotel, so we want to make sure that people get home on time and safely. Thank you.
Okay, thank you, Chair. Mr. Chairman, thank you so much for the opportunity to have continue to engage on a platform like this to discuss critical issues around measurement. I would like to stand on the existing protocols to continue the presentation as fast as possible. Please, I'll skip my profile, and then we'll move to the next stage. Next slide, please. Next slide, please. Well, basically, I would want us to look at the theme of this conference, and that is unlocking gas resources. But we need to first of all understand the production value chain. And understanding that will give us a better idea of how measurement should be carried out. And from there, you ask yourself questions. If you're able to implement that, how then do you move to the next stage of taking advantage of the information that you have for digital solutions? And that is why everything about digitization is quite important, except if you have the sensor at the base very, very, very good. And then we'll talk about the metering or measurement landscape, of course, as it relates to process. Then I will talk a little bit about well-led multi-phase metering, because we need to understand the production valuation in terms of measurement. And then talk about focusing in this case now to wet gas, because the theme says unlocking gas resources. That means that what we are doing relates to wet gas application and directly gas condensate wells. And then we'll talk about in certain areas of the process measurement, the impact of entering gas in some meters, especially Coriolis. But what has been done in terms of technology to improve that, so that your measurement mass balance from wellhead to custody transfer is well accounted for? Because when you're going for reconciliation, for example, I mean, regulators receive petitions here and now because of reconciliation issues. Who is producing more? We should get more revenue and all the rest of it. But even before you go, you should be able to tie your plant mass balancing very well before you go, because it's a closed system. And if you're losing production within your facility, you shouldn't go for reconciliation. And don't even think of, petitioning your other producer or something. Don't do that, because your measurement, parameters within your facility is wrong, because you have not deployed the right measurement solutions for the application. Next slide, please. So, I mean, this is just the classes of measurement that we have as of today. But there is one leg that is red here. The question is, are we going to have another measurement class soon? Or should we continue to discuss that as quick as possible? And that is continuous emission monitoring solutions. Of course, we do FLE, and then FLE measurement is on class D. But again, we do FLE. The question is, what is the quality of FLE that you have? What composition? We only do the volume, but we don't know, the contamination, the contaminant in it. Okay, if you go to class C, we talk about fuel gas monitoring, measurement. Fine and good. Then you supply fuel gas to your gas turbine generators in your plant. The question would have been that, okay, what is the emission at that point? Because the commission chief executive, when he goes out to meet, global audience, he will begin to talk about how we are reducing flame. But again, you also need to talk about the quality. Again, at the presidency, maybe at the SGF, or we have our minister spoke earlier. Okay, what is the quality? Because you have to talk about decarbonization. But again, what is the quality of emission that we are talking about? So that when you are talking at global stage, you'll be able to tell the people that, look, we are taking accurate measurement and analysis of the flare that we measure, and this is the quality. Don't come and tell us we are not doing the right thing. We should have a voice to speak, but with data. Next, please. Okay, this is a typical process flow diagram, and it shows the different measurement points. And this is for gas condensate well, an example. The thing is that we have well-led measurement, and that is multi-phase, in this case, wet gas measurement. And then we have process measurement, process meters. Of course, down after stabilization and removal of water, dehydration and everything, you now have physical measurement, because you have the quality of gas that is needed for export or for local consumption, what we call domestic gas. then that goes to power plant and everything. You must meet the quality, the specification. So next, please, I will be fast. But this is my experience. You know, I've done flow measurement from wellhead to custody transfer, allocation, physical metering. So the question, there are different technologies when it comes to wellhead metering. But again, why wellhead metering? Because we want to have so much data, and this is where digitization is where we are driving digitization. We used to have separator for well testing, you know, but it's very expensive, risky. You know, it doesn't give you the right information about your well, the health of your well, or the productivity index at the end. So, but you have an inline meter that gives you the three-phase measurement, gas, condensate, and water. So at every point in time, you have good information about the flow regimes, or you can predict, or you are seeing, because you have the trends that shows that this is how your gas is being produced. And at a certain point, okay, water is beginning to come into your well bore, and then you should be able to plan for well workover operations and everything. So you have, I mean, pretty good information and data about your well performance, and as well as predict your reservoir, you know, depletion. Next, please. So in general, this is, I just want you to, please, press it again. Yeah, it should be a video. Okay, so, but this is an experimental video from CC. If it's playing, you will see. And this is simulating wet gas at a certain gas volume fraction and water, you know, liquid ratio. At 100%, and of course, the other one at 30%, you will see the behavior of this, and this is laboratory condition. It is never stable. It is never the same. Just picture that. Under controlled environment, you will have this type of behavior. When you go to the field, what is happening? At high pressure. So, and that is why instrumentation is very necessary. Smart instrumentation, a reliable one, because whatever data you are pulling to form the basis of your digital transformation is as a result of this information at the base, at the field. And if it is wrong, whatever you're saying is also wrong. And your reconciliation process is also, you know, already wrong. Next, please. So this to show you the flow regimes, whether for horizontal and vertical flow environment. The truth of the matter is, for wet gas, you can only operate at this side of the envelope for horizontal. And for vertical, you can operate at this side of the envelope. This side to slug flow, and that means is either annular or mixed flow. For slug flow and downward and everything, it is more suitable for traditional, and this is where I'm going to, multi-phase meters. It is not for wet gas application. I have seen a scenario where traditional multi-phase meters manufacturers or supplier will tell you that I can also do wet gas metering. It's not correct. Because the envelope to which their multi-phase meter on the gas volume fraction is tested could be 5%, but 5% is 100% on the data sheet. Yeah? Because it is not 95% tested. When you go to the field on gas condensate, where what you're seeing is like 99%, 95%, 96% of gas with some amount of liquid that impact the measurement. Or as you further go down the production downstream, you know, pressure and temperature variations, and then condensate come out of the gas phase a little. And then that should form the basis of your, you know, mass balancing with accurate measurement. Next, please. I'll be very fast. Next. So, I mean, generally, studies have been helping to the extent that we now know if you're talking about wet gas metering, to properly unlock gas resources in the country, we have to look at it in 3 different types. And that is a definition on what we call an equation called Lockhart-Martinelli parameter. And that parameter should at most be equal to 0.3. If it is greater than 0.3, it is a multi-phase flow regime, not for wet gas application. And this is where regulation comes in. The question is, any multi-phase meter manufacturer can come and tell you, I can do wet gas metering. Please, can your multi-phase meter withstand a lockout Martinet parameter of less than 0.3? If you have less than 0. Or equal to 0.02, it's categorized as type 1 because you have very small amount of liquid. And that is why we talk about all these things process-wise. You know, sometimes we discuss and some people say, oh, my well is dry. And I say, sorry, you don't have dry well. There's no dry, okay, they say dry gas. And I say, sorry, you don't have dry gas wells. It's the degree of wetness. So there is still some amount of liquid, so it's still wet. But that affects your accounting processes downstream. And how you are able to take care of this matters a lot. As at present, I don't know, maybe it exists, but to the best of my knowledge, there is no multi-phase guidelines for Nigeria yet. It might be in the pipeline, or it might be something regulators are looking at. But if we are to critically look at it, we need to differentiate what a multi-phase environment is and what a wet gas. That's why I define it. If you look at it, I said wet gas is a subset of multi-phase flow in which the dominant fluid is gas with some presence of liquid. So we need to characterize it very well because it is what guides every producer to select a technology. Otherwise, everybody will bring a multi-phase meter and say, oh, I can do wet gas. Oh, a wet gas meter cannot do a traditional multi-phase metering environment. It cannot perform for crude oil or for liquids because the models for traditional multi-phase metering is on the black oil models, which they use in reservoir simulation and analysis. The density of oil is different. The viscosity is different. So if you take that into the model of wet gas, it will fail because it is seeing different density. And the PVT is also different. So that is why it is different. Please, next, I will be very fast. Next. So, I mean, the best, I won't say, but I mean, there are different technologies, but my experience, it's on Venturi. And that's because a very experienced man called Rick Delu from Shell, is retired now, did a lot of work, extensive work, using the Venturi to measure wet gas. And he found, at some point, what we call pressure loss ratio, PLR. And that's the differential pressure across a certain length of the Venturi divided by the differential pressure of the Venturi across the Venturi throat. And the Venturi is designed in such a way that when the differential pressure comes in at the Venturi throat, you have a DP, but when it is recovering, it is not recovering fully in the pipe until a certain distance. So they have studied it at different points to the fact that they have now at a point where they notice that the differential pressure across the Venturi will be able to, this PLR will be able to indicate to you the amount of liquid in the flow stream. And that means the density, if you're using, I mean, these are differential pressure flow instruments, the same as orifice, but for single phase. So if you begin to load liquid in it, you'll find out that the gas become heavier in terms of density. So it means that there will be an overreading on the DP because of the weight. So the same simple differential pressure flow instrument equation is used, but they now have to use the PLR to be able to have an indication of the liquid in the flow stream so that they can, use that one in the model advanced algorithm that they have developed to be able to output the three-phase for you, as accurate as it should be. Next, please. So, I mean, this is some function blocks for some, deployment. And you see that the foundation is the input parameters. It's just differential pressure and pressure transmitters. But what you see is the pressure loss ratio, which we just saw, and then there's a PVT model, and then there's a wet gas correction model, which gives you, in that to give you the three phase. But what is important is the PVT, the PLR. If your pressure instrumentation is not accurate, then your PVT measurement or calculation or model is also out of range. So that's why smart instrumentation is we are building to digitization. So that's why smart instrumentation is very key to unlocking gas resources that we have. Next, please. So the next one I'm going to talk about is process measurement. And I'm talking about in the process flow diagram that we saw much earlier, we saw that there are places where you have a slug casher because you still have to stabilize a little bit of your well stream. So in your slug casher, you have, of course, your gas phase, gas leg, and then you have your liquid leg. Then you have to measure that volume also because you're doing mass balancing. And this is where process mass balancing comes. It's very important before you go for reconciliation. Remember I said that. And so in your liquid leg, it's condensate you have. Condensate is also a bit lighter, for example, compared to crude oil. So the density is also light. But because you have slug casher and you are not, what is the retention time? It's very small and it's gas. It comes in, it goes out. If it is liquid, the retention time could be like 120 seconds, there about 90 based on design. And then it can stay for a little while. There will be a little bit of separation or stabilization that you will enjoy. But for gas, that's why test separator is not really suitable for gas well testing because it comes in, there's no stabilization, it goes, and sometimes it comes with bubbles in the separator, and then there is bubbles, of course, in the gas leg or in the liquid leg, but you have to measure it. What technology are you using? Most efficiently is Coriolis. The question is, gas bubbles or entrained gas is also being affected, affecting the measurement of Coriolis. But again, advanced, research has also improved the measurement using Coriolis meter, and that is why it is very important. What we are talking about today is having smart instrumentation for digital improvement. Please, next. Next. Yes, next. I'll be very fast now. Next, okay. So this is the conventional Coriolis meter technology, where you have your sensor and then you have the driver. The truth is that, and this is simple and well known for everybody, the sensor and the driver are connected in one block directly for traditional Coriolis flow meter. So it means that whatever the phase shift or the frequency of movement is translating into the driver. So if gas bubbles comes and distorts, the frequency and oscillation, it is directly feeding into the driver. And that gives the measurement output of a Coriolis flow meter wrong when there is entrained gas. Next. I think I just have like 2 minutes, I will run off. Next. Yeah, so, okay, go back a little. Go back. It's okay. So now, in this case, you find out that, go back a little. You find out that you have the transmitter now digitally connected on a digital processor. So what happens is that the conditioning of that phase shift, of that impairment because of entrained gas, is being processed and then dampened in the electron, is not transmitted to the driver. So the resolution is in the internal of the transmitter before it goes. I would have explained it much more better, but because of time. Next, please. So it's not directly coupled, to the driver. Next. So digitization, why do we need to implement that? I want you to look at this. This is a typical production envelope from startup to when you're at plateau. But the thing is, we need to understand that every gas production is tied to a contract. Either you are supplying to export or you are meeting your domestic obligation. It then means that your compressor that you size, should be able to handle that. The question is, for how long? Because your choke opening at the wellhead is dependent on the demand from your downstream customers. So if the demand high, you also have to open your choke because you need to meet the contractual obligation, is it not? So it means that for the gas wells, the plateau is very short. And the commission chief executive spoke, and he talked about those who are not able to meet their field development, they will be delicensed and issued to others. Question now is, what is stopping you from producing that? Because some of them want to discover some other gas fields so that they will be able to have enough compression capacity. So if you have 1, 2, 3 wells, you might not want to go and put compressor because it's not economical for you. But again, we need to discuss about how we can now do fiscal allocation from the wellhead to maybe a third party. You have to deplete that gas well because we want to harness our gas resources. That means you can actually use a multi-phase meter, wet gas meter, to produce at the wellhead and maybe send to a third-party processing facility at an agreed accuracy rate where revenue is tied to the gas phase, not the condensate phase, or not the water, because it is small. So this is the question. This is why we are talking about technology, because at the end of the day, this builds up to the commission having remote monitoring and command center, because they will have to gather all this data. They have to be seeing it. Before you come and petition somebody, they already have the data and they are waiting for you. So when you come and begin to say, I want to petition Mr. A or Mr. B, they have substantial information to be able to ask you questions. At so and so time, your wells were down, or your wells were producing at this rate. How come you say you're producing more than Mr. B? So you have to ask questions because the trending and the information are already there for them to see. And this is where we are going to. Next, please. Next. I'm done. So you see, it's just building from the field instrumentation. This architecture is very necessary, to the controls, and then to the application and software where you'll be able to have dashboard. Next, where you'll be able to have dashboard. Next, please. Where you'll be able to have dashboard to be able to quantify which well is producing well, better, and which asset, is saying I am getting more than the other person. Thank you so much. And we look forward to questions. I appreciate it.
Thank you, Dami. Thanks. I used to think I talk too much. I've seen somebody that passed me. So before Secretariat, is Sheriff from Dubai is ready now, or we'll go to the last speaker, Mr. Lazarus? He's not ready. Okay, so the next person will be talking on sand metering and natural gas optimization. And again, all this discussion today, we're going to wrap it up tomorrow. We have heard a lot of emission and venting. So NIMEC, in their wisdom, is introducing something new that's going to whet appetite, which is on carbon capture, utilization and storage within the contents of greenhouse gas effects. So please make sure you're here tomorrow, and I'll be doing that with my good friend, Dr. Femi, in this room. So one of the things we're going to see is something that continues to reverberate and why we have to walk and walk safely. So with the permission of my fellow discussant, I would like Mr. Lazarus to have the floor, and please keep to time so that people don't get slip up. Thank you.
Thank you very much. I will try my best.
Please.
Okay. Good evening, ladies and gentlemen. I think we're already in the evening. Still afternoon. Okay. My name is Lazarus Musa, Managing Director of, I'm sometimes afraid to mention Managing Director. but it's okay. And then let me also start with this. You know, they've always said that life is not balanced. Okay? Because when I was down there, I was enjoying the screen, but when I got up there, I wasn't seeing anything. So I just concluded life is truly not balanced. Is that okay, everybody? So, all right. Thank you very much. So standing on the existing protocol, I will be talking on sand metering and natural gas optimization. Okay, so go to the next slide. Okay, so sometimes back, this was the scenario we had, and then move on. And then we woke up on inauguration day, we were told no subsidy. And then we started seeing some stations, calm down, bro, calm down. Started seeing some stations, somehow you would think they don't have PMS, but they do, but just that maybe the price went high. Next. And so the issue of compressed natural gas now came up. So federal government, state governments are now embracing CNG because of the cost effectiveness of CNG. Next. And so, having said that, we know that there's going to be increase in natural gas output, more revenue for federal government and the E&P companies. There will be increase in repairs and maintenance costs for wells, more opportunities for service companies, and more opportunities for auto mechanics and CNG vehicle conversion part dealers, because that is going to come up big time. Next. So there's no way you increase volume actually without associated solids, and which will lead to equipment wear and tear, like your chokes are going to actually wear out, your valves, flow lines, everything will, you'll have your vessel sanded up as you continue to flow. Next. Then, of course, when sand comes, you lose revenue because you lose production, and then you begin to have unplanned maintenance. Next. So these are the factors that are responsible for production. One, increase in gas velocities. You can't overlook that. Number two, you know, we produce from less consolidated reservoirs, so definitely you cannot do without sand. It's as simple as that. A lot of people overlook it, but you cannot do without producing the sand. Then we rise in demand for natural gas, LNG and CNG will lead to that. Then again, we also have this issue of quickened payout time, because a lot of people, companies will want to say, oh, okay, now that we have opportunity, let's see how we can make quick money. So the temptation to make quick money can be disastrous. Next. So before now, and we have so many control measures. Apart from the subsurface exclusion methods, there are these surface control measures, fluid sampling, your BS&W, and so we also have the pressure drawdown control. People go try to, you know, adjust chokes from time to time. Coupons and erosion probes are used, sand traps and filters are used. But one problem with the sand traps, especially when it comes to the sizes of mesh, there are some sand sizes that are smaller microns, and you can't catch them. And they are still very, very dangerous. We all agree with that, right? Okay, so, and then we also have the acoustic sand detectors or meters. And that is what I'll be talking about. So in this case, actually, we're looking at a meter, which is an acoustic device that can actually measure sand. This is how it's being installed on the flow line. They are real-time, non-intrusive, installed on an elbow. They are installed downstream. They can come in form of portable or permanent devices that can be installed and integrated into your SCADA system we're talking about automation here, so it's you can have that. So move to the next. So if you see the picture here, you can actually have values flowing on a screen like this, and you can actually see what you are producing. So, and there are several technologies out there still talking about the acoustic sound detectors, but we've found the stress wave sensing actually really doing better than others, okay? And it is based on that. So you can have measurements. In fact, even within, maybe you have a flow velocity of 0.3 meter per second, it will still peak, you know. This type is auto-calibrated. It self-calibrates itself. You don't need to go into the rigors of trying to calibrate all the time. And then it goes beyond trending and it's able to quantify your solids for you. It's resistant to interference. It's not affected by background noise like others are. And then it's able to, sorry, that's not able to study. It's just able to store log data for 90 days or more. All right. So, and then suitable for multi-phase flow. So it means in this case, whether it's gas, whether it's oil, whether it's water, whether it's wet gas, whatever it is, it doesn't care, right? Okay, so it has a working principle, like you can see in the other picture there. Yes, you install it actually downstream of the flow. So assume a particle of solid is flowing and it gets to the bend, hits the bend, an electrical signal is peak transmitted from the sensor down to the controller. And then the controller does the analysis and give you results in mass and sometimes in rates, gram per second, and so on. Then, of course, what they were able to do was just to be able to get those who are in instrumentation or the mechatronics, you call them, who were able to say, okay, there is a narrow bandwidth that this is operating with. So that makes it actually able to get the frequency of the sound that is made inside the flow line. It picks it and it's able to distinguish it very well. Okay? All right, let's move to the next one. So, and you can actually present your data graphically as well, because as you have them, you can download the data, you can plot a graph, you can check the trend, you can see what is happening actually to your well and be able to predict what happens with your reservoir. All right. And then this is the units of measurements. Okay. So go back. Okay. So, and then the equipment, go back, sir. Okay. So you have this. This is the device unit of measurement. So you have impact per second, which gives you the trend, grams per second rate, and then you have grams in weight. And then the screen you're seeing there is actually the screen it comes with. So you can see that right on top of your controller. And then we also have these calculated units because the devices don't come with our traditional field units in pounds per 1,000 barrels or pound per million standard cubic feet. So 2005 actually got a conversion factor. I published it in SPE 2005. And then we use that to get our measurement in pounds per 1,000 barrels for the client anytime you want your figures in pounds per 1,000 barrels. So go next one. So now this is a case study. This is a case study. Operator not mentioned, but it was actually a sand-prone gas well producing lots of water and condensate. But because of the theft and all of that, the operator didn't have where to store the condensate because you cannot push the condensate to your export lines. It will be tapped. And then when you're trying to do that, maybe Shell or whosoever owns the trunk line will say, please, you better shut in. But then the gas was needed. So we were called in a situation like this. And before then, now this was the wellhead pressure, about 1,539 PSI. And then the gas rate was like 35 million standard cubic feet, you know, and but was making 297 barrels of water per day and 439 barrels of condensate. Now, there was no sand data then, but the operator actually wanted to see how to optimize the well. But then the fear of what if we start making sand, what will happen? So we had to go in, and then by the time everything ended, now they were able to actually control the well and reduce the level of water to this time 33 million standard cubic feet. The water rate dropped from 290 something to 85. And then the God condensate rate, you know, increased somehow. But that actually was like, at that point, they needed the condensates. Something has happened. And then they were comfortable producing. And then we were able to also get the sand production for that period, an average of 0.4 grams. Now, that actually increased the confidence level of the operator. He now knows I can produce this gas well without the fear of producing sand. Move to the next one. And so actually, when it comes to acoustic sand detection, the API RP14E document actually covers it. Somehow based on erosional velocity, but there are some of these parameters that were not considered. They didn't take account flow geometry, sand size in microns, sand composition, the Reynolds number or pipe roughness, all that wasn't considered. What they considered in that document was basically the flow velocity. And almost everyone trying to bring up sand monitoring equipment based on acoustics, we want to refer to this document. Move on. So what are the consequences when we do not measure sand in our natural gas wells? Erosion of equipment, formation damage, workover cost, loss of production, safety issues. We all know that. I don't need to break it down anymore. So go to the next one. So my conclusion is like an appeal. Yes, it's an appeal. The regulators were being hit right, left, and center, but I don't want to hit you. No, I'm too small. I'm too small to do so. I'm too small to do so. But the truth is, sand measurement is serious business, obviously. It's serious business, especially now that we are getting into gas optimization. We're trying to unlock our gas wells. Those who had decided, who before now had locked up their wells, nothing, they are not ready to sell, not ready to produce. Now, the market is opening up now. And then, since it is a big business coming our way, so we want more, the operators, obviously, to pay attention to best practices. There's no way you will flow even your oil wells without paying attention to the sand production. Why are we even talking about metering here? That you go once in a while and collect sample from the wellhead, go and analyze, does not give you the full picture of what your wells are producing. Honestly. So in most cases, let me just give this little testimony. I was in a particular place offshore, and I went personally, and I did a measurement, and I gave this operator the data. They said no. They went to collect sample. They found nothing. They went again. They found nothing. They said I was lying. I said, okay, I've been using this for years. I will not tell you I am lying because I will not accept that I'm lying, but just keep the result. 6 months after, the whole offshore platform shut down. And then when they were now investigating, they now found out that it was that particular well that I reported that was the culprit. And they found all the wellhead restrictions were eaten up, and then everything, pumps broke down. Okay, so then I want to appeal to management to channel resource management of the EMP companies. Please channel resources to mitigation than cure. I believe so much in preventive medicine. In fact, even my children don't fall ill of malaria because before you fall ill, I would have given you a malaria medicine on my own. And the doctors actually agreed with me on that. But so I also want to appeal to the academia to expand the scope, because somehow, you know, when you get to the universities, you don't, yes, they take you on metering, but they don't go into most of these automations. And it's affecting the quality of our, you know, graduates, okay? But I was happy. One lecturer met me during that NAIS program and actually was asking if I could come and do a presentation for their students. And I was glad. In fact, though he hasn't called me. All right, so, so what also say that, lastly, neglecting solids is financially and operationally detrimental. There, I will beg to stop. Thank you very much. Did I take time?
No, Thank you. Not. Just in time. All right. Thank you, Mr. Lazarus. So I had similar experience in the past. When you run a test, it's an instantaneous test, and you don't run a test for 24 hours. What you do is 4 or 6 hours test, and then you prorate it over 24 hours. There is erosion velocity. And I've seen over and over, even when I was working in CAFG joint operation in Saudi Arabia, which is highly sulfide field with sand. The destruction of sand on the wellhead is unimaginable. But that's just, you want to test a well to make recommendation, but you don't want to test your children before you issue malaria drug. Okay. So that seems to be a contradiction. So we have to pay attention to that. All the chokes we go, and then you have to replace all those chokes. So it's a serious matter. So on that note, Secretariat, is Sherry available now from Dubai? Amin is back to handle it. Is he ready? Huh? He's up now. Okay. Okay. Is it Amin or Sherry that is speaking? Amin. Okay. Can you give him the floor?
Do you hear me?
Thank you
Hello?
for your patience, and I know it's late in Dubai now, but that shows the level of importance you attach to this program. So you have the floor now to go on. Although we are behind the screen, we are not seeing what you people are seeing. Live is not balanced.
Okay. Hello, everyone. Do you hear me? This is Amin. Amin, is that my turn?
Yes, we can hear you. Go ahead.
Okay, good. Let me go ahead and share my presentation. Okay, where am I with that? It is not sharing. Okay, sorry for the delay. Just 1 second. I should be on right away. I guess you see my slide now. Hello? Hello, yes. Good evening, everyone, and thank you for the time to sit through this long day and listen to my presentation. I send my regards from Houston, Texas, and my talk today is about the application of data validation and reconciliation to upstream production, measurement, integration, and surveillance. And we will be, I'll present the technology and also a field study on that. Basically, the content of my presentation is to introduce the concept, which is not that familiar to many, of data validation reconciliation. That's a modeling concept similar to simulation, but it is not exactly that approach. And we will mostly focus on upstream applications. We'll talk about the DVR technology, and then we go quickly through the field case study where the system is being implemented in the North Sea, and show some of the applications of that system in that field in terms of virtual flow metering, integration with multi-phase flow meters, the equipment and process diagnostics, and some sort of a soft sensing. Then we look at the concept of real-time implementation, then leading to summary and conclusion. In words, what is data validation and reconciliation in words? Let me read it through slowly. Data validation and reconciliation, DVR methodology, actually, is a first principle equation-based calculation process. It uses all variable information. That means all information available within a process, which is, in case become redundancy, and conservation laws to detect and correct measurement errors and convert them into a reconciled data set that statistically best represents a process. Now, that approach is used widely in many kinds of processes, from refining to gas plants to power plants, mostly also in nuclear plants. But in this particular presentation, I'm going to focus not so much on the upstream, on the downstream and power plants, but more so on upstream. And for upstream, there are a number of applications that are can be beneficial from this core engine, modeling engine of DVR. In particular, it enables surveillance of real-time facilities for health check and optimization. It does provide metering concepts such as virtual and multi-phase meter monitoring and validation. And the measurement quality side, it detects bias of measurements and uncertainty, leading to uncertainty reduction of the measurements. It provides for defensible allocation by bias identification before performing the allocation, production allocation. It does design optimization to reduce CapEx, operation efficiency improvements to reduce OpEx and non-productive time, and certainly leads to, because of the redundancy, leads to process uncertainty reduction and also uncertainty propagation to estimate what would be the uncertainty of the outcome of your measurements. Overall, it is really, in a sense, a physics-based digital twin of any production chain from sport to process, and that is applicable to either and wellbores, surface facilities, and what have you, and integrating all that data, as we will see in the case example. To just quickly go into this concept of DVR, I know in comparison to conventional process simulators, DVRs add statistical component using measurement uncertainty and redundancy. As you see, the concept of uncertainty on the left-hand side, which consists of the uncertainty or precision, signifies that really there is no measurement that is 100% correct. An expectancy range is always associated with the measurement 95% confidence level, as shown on the bell curve on the left. On the other side, if the instrument is off calibration or the wrong fluid sample is used, a bias is introduced. And often bias is hard to detect and can change or drift with time completely unnoticed. Any process is often impacted by the combination, as we see here, of the measurement precision and bias, primarily bias. I mean, what if your sensors are drifting and you don't know they are? And that's where this technology or this methodology can help detect these kind of biases. But in order to do that, it has to rely on the wealth of information that resides in a given process. And let me illustrate that concept of redundancy that I show on the right. This is an illustration. What I show on the right is an illustration of a simple 3-variable example, which consists of one equation, which is the balance of what goes in and comes out. That is A equal to B and C, or A minus B and C should equal to 0 from a material balance perspective. And 3 variables that if we measure 2 of them, let's say we measure A and B, then in simulation approach, we would calculate what would be the variable C. But eventually, what if on top of calculating the variable C, we also measure C and find that there is a difference between what we calculate from A and B and what we measure with, say, a flow meter on C. In this situation, we have what we call a redundancy because we measured C on top of the 2 other measurements that were sufficient to calculate C. Once we have that redundancy, we have to be able to reconcile what we measured with what we calculated. And that's where the concept of DVR comes, by using a layer of statistical layer on top of the process to be able to perform that reconciliation using the added information from the added measurement that you did on the parameter C. With this, I would like to illustrate how this is done compared to a conventional modeling that's using straightforward process simulation. Let's start by quickly describe what a process simulator is and compare it with the DVR. A common simulation workflow consists of data capture system, which is a database, as we see on the left-hand side, a calculation model based on equipment and fluid models, as we see in the middle here, then the projected or calculated results as we move back from the database to the right. So basically, we have some sort of a one-way calculation that take the measurements, the models of calculation, do the calculations, provide the outputs, and you have now a projected calculations for the variables that are either measured or unmeasured. In a typical process simulation workflow like this one, the model uses a limited set of measurements because we basically use the measurements at the input and the equations to calculate what goes at the output. The calculations also are done in a deterministic fashion without accounting for measurement uncertainties. So if the measurements have errors into them, really we only take the measurements at face value, and we do not care too much when we do the simulation as to what level of uncertainty or expected uncertainty is around a given measurement. Plus, the raw measurements are used without consideration of potential inaccuracies can be due to measurement bias. That means if we take the measurement at face value and there's a bias, then undoubtedly that bias is going to propagate all the way to the output calculation, and your output is going to be also biased if you have not spotted this bias before you perform the simulation. And furthermore, redundant data that can exist, more measurements, as I showed in the example A, B, and C, like, we have a measurement of parameter C on top of the calculated one, that redundancy is not used in the simulation approach. In fact, if you use redundancy or this added information, it may generate overspecification error if ingested in the model. Now, how does that now differ from a DVR approach? In the DVR approach, we add what you see here is the red overlay that represent the statistical layer, okay, the statistical layer, and the iterative process that generates the reconciled value, what we call the reconciled recalculated value. So basically for each measurement, what we do in this loop, we take the measurements before we do any calculation to the end point. We perform a convergence or an optimization of what we call an objective function by making automatic changes, small changes to each of the input and output measurements, all the measurements in the system, until all these measurements are satisfied, or the reconciled value of these measurements or the adjusted value of these measurements are satisfying the set of equations and physical principles are derived or described in that process. With this loop converging, then we have a new set of values for each measurement that we call the reconciled values. To the extent that these reconciled values are close to the original measurements, then we do not have a bias, or we have pretty much a matching process. But if happened that some of these reconciled values are in mismatch with the certain measurements, then penalties are flagged in the process, telling you where potentially there is a bias or drifts in a specific measurement that you needs attention to go back to correct. Okay, so once this process is corrected, because you cannot really calculate things with biased information or incorrect information, then you would correct the information and then perform the same iterative process to now arrive at a set of reconciled values that are much more representative, as I mentioned earlier, than the original raw measurements that you started with. And that's really the beauty of DVR, is that it does not take anything for granted and calculate with it. Basically self-check the health of that measurement and the process and the relations between these measurements before it proceeds with giving you the final representation of that process. With this in mind, if you bear that in mind, then I would like to very quickly highlight in 2-3 slides what is a potential application as has been applied in one of the fields where the system been running now for a number of years, almost 9 years, on this platform or 2 platforms that I show in this graph in the Amistil field in North Sea. That's from Neptune Energy. In this, I show a setup of a facility that consists of a satellite platform on the left, that's Q13A, and a production platform here, the separation platform, which is about 17 kilometers away from the actual satellite platform. Now, it happened on the satellite platform on the left, which is represented in the yellow process diagram. We have 4 wells producing that are shown here with the header for these 4 wells. And these 4 wells go into a header that is being tested by a multi-phase flow meter. And each of the wells is sequentially passed through the multi-phase flow meter to be tested. And then, of course, the production of these wells is being put back into the production header, into a separator to take off the water and inject the water in the well, injection well, as we see here. And now the gas and oil or the hydrocarbon is being pumped into that pipeline of 17 kilometers all the way to the final separation and sales facility, where compression of gas takes place and the separation of oil is done, you know, with the gas and solution coming out, separated, put in the gas line, and then the final measurement of the physical measurement of the gas and the oil. So this is quite a lengthy one, but let me take your attention to the left one in red, which shows the actual well components from the sand face or the perforations.
Hello,
into.
Amin, you just
Yes.
have 5 minutes to round up, okay?
Yeah,
5
I'm
minutes.
done. I think I should be done in
Amin, did
2
you
3
copy?
minutes.
5 minutes.
Yes. And
5 minutes, please.
absolutely. So with your attention to this particular each of the wells, we're actually incorporating the measurement of each of the components of that well, which is from the inflow performance to the pump to the tubing performance to the choke, with each of them giving us an information about the flow rate in that particular well. The DVR process takes all these different information and consolidate that into one single optimized flow rate. That's a virtual flow metering done through the DVR process to give you an estimate of what that flow rate and as it compares to the multi-phase flow meter. Okay, so that's a concept of using DVR for metering and to validate and to compare measurements from different sources with the actual physical measurement from the multi-phase flow meter. So this is a validation process. In one case, the meter was off track and there was a problem with it. The validation was continued to do the to perform as it should be from other measurement sources. And we see that when the meter was put in operation, these measurements were aligned. In this quick example, we had a problem with the 2 performance curves of the ESP on the well, and the ESP was giving us penalties shown in red here, indicating there's inconsistency between what the model is calculating and what the ESP performance is. Turned out that the ESP was wrongly, the wrong ESP was put in the wrong well, because when we compared it to the other smaller size ESP, found out that they switch actually similar ESPs in the wells and they have to retrieve one of them to put it back in the correct well. Similarly, we had problems with you remember the fiscal meter of the gas, which indicated by penalties between what the model was measuring compared to what the actual measurement, drifting on that meter and highlighted by the red highlights and shown in penalty. Similarly, flaring, that would be a soft sensing. The model by itself can minimize the requirements for actual physical meters that could be costly by using all the information of the process to give you a good estimate, for example, for the flaring on that particular platform. That said, the implementation of the system is pretty much in the form of the engine being implemented on one of the servers, interacting with different databases to collect on a real-time that information data, perform the processing reconciliation, and then put back that reconciled or more trusted reconciled values into the reporting system for further archiving or use for decision-making by the actual customers. So that's basically a self-contained system within a given process. The whole thing is not new. It is in development over the 35 years, and with the certification of the actual calculation optimization based on standard from the German engineering certification VDI 2048. With this, let me remind ourselves of the use of DVR for that integration as I started with. So what I talked about today is an introduction of DVR methodology in upstream to enable upstream data integration through surveillance and real-time monitoring for allocation, virtual flow metering, MPFM validation, for early detection, in particular, of biases, for predictive intervention using the concept of penalty of measurements, okay? And basically also perform design optimization by minimizing the requirement for physical measurements where that can be done. Use it for also economical multi-phase measurement solutions to give you also a live model-based digital twin of your process that continuously monitor the process and give you that predictive information for action, and give you finally a confidence in the decision-making using finally a trusted data that is not corrupted by biases or errors as the raw data may be. Thank you for your attention, and if there are any questions, if the time permits, I'm happy to answer or answer it at a later time. Thank you.
Thank you. Thank you, Amin. A round of applause for him. So be online. We might have some questions for you once we take the last presenter today. MC, go ahead.
All right, Mr. Chairman, thank you. We would like to quickly invite Mariam Idrisu of Emerson Automation Solutions to please join you on the panel. If she's on ground, please can you put your hands together for her? I'm very sure the organizer has hinted you, and over to you, sir.
Thank you. Thank you, Maria, and thanks for being part of this event. So the last is going to be on strategy, challenges and solution in a brownfield operation by my friend Longinus and Njoku. Please, 15 minutes. If you give me less than that, I appreciate you.
Thank you, sir.
Thank you.
Good evening, ladies and gentlemen. Glad to be in your midst to present my slide today on behalf of Aradel Holdings PLC. Please, can you quickly present the slide? By the way, I am the maintenance coordinator and equally in charge of metering for Aradel Holdings. And I'll be speaking to the metering strategy, challenges and solutions in a brownfield facility. And that will be based on our experience on the journey so far. Let's have the slide, please. All right, let's go to the next. Because of time, let's go further. Okay, we all know, actually, I'm here more of to tell our story as Aradel and as an integrated facility, because as an integrated facility, we have a journey. We came from somewhere, and about 18 years ago, the facility was barely a flow station of 10,000 barrels capacity. And then today, the facility has expanded and transcended to a 20,000 processing capacity of flow station, 100 million SCOF processing capacity of gas, and an 11,000 processing capacity of refineries. And so you can see that we have a whole lot of expansion and the bottlenecking projects, and it requires a strategic approach to manage the metering processes. If you can go to the next slide, I would like you to have an aerial view of our facility. So if you look at our facility, this is an aerial view of it. You see that everything is put together. At the center here, it's not so clear, is the flow station. And by the left here is the gas plant. And by the right here is the refineries. The extreme left is our product processing storage tanks. And we actually have our loadout station here, our product loadout station. So if you look at this, first of all, the flow station processes crude oil. And when it processes crude oil, it is stored in the storage tank for export. After the export, part of it is equally sent to the refineries for processing. Then the associated gas is sent to the gas plant for further processing. That is the flow station for you. And all these things have to be accounted for wherever they are coming from and where they are going to. And then at the gas plant, it processes this gas and we use part of it to fire all the heaters we have, both at the gas plant, at the refineries, and at our power plant, power generation plant as a fuel gas. So, and it is important that whatever you produce, because what is not measured cannot be accounted for. And if it's not accounted for, you will not be able to verify the uncertainties. So we have a strategy, and the strategy is to have metering points at various exit of all these facilities, such that we can account for each and every molecule that we produce or we process. And in doing that, we have a whole lot of, that's the strategy in the first place, and which I would like to speak to. Please, can you go to the next slide? So the first one is, of course, part of it is interdependency in processes and production balance, and of course, this evaluation of uncertainties. And then another one is we have to deploy an integrated solution to measurements, because as we evolve with time, technology equally evolves. We have to use the three. I think most of the speakers have actually touched on most of my presentation here, because it's all about the principle, but what matters is how you manage yours. But we use people, processes, and technology. So initially, we have more of pneumatic means of control, instrumentation, and measurement. But now we have to deploy a more evolving technology so that we can actually evaluate our performance and then our benefits too. So at Ubali, we use different type of meters, PD meters, turbine meters, Coriolis, magnetic, thermal, vortex, and ultrasonic. And of course, each of these meters have come with their own challenges. But it's just that all those challenges are things we actually manage, but we really have to manage it to advantage. So part of our strategies is to continuously review the critical metering points. So we strategically identify metering points on all the exits of all our production processes and install meters there. Because as we upgrade the facility, we equally upsize, we equally identify the metering points. And a whole lot of things are involved in installing new metering points. But after that, the next is we analyze, because don't just select a meter. A whole lot of speakers have talked about it. You must analyze the economic benefit of the meter you want to install with respect to the cost, the performance, and of course the services it renders. So we analyze the economies of scale or the economic benefits. The another one is that we reevaluate our metering systems. We continuously embark on reevaluating, just like the last speaker said, all our metering facilities, check the uncertainties, and check where they are viable. Where they are not, then we are bound to or recommend replacing these meters. And that is why, even as we are here, like I said, I'm here to tell our stories. That's why OEM and vendors will now come and unlock. It's a way of unlocking opportunities and where we can have mutual benefits on managing the areas we can share common interest. So the next one is, of course, we select appropriate meters. And then these are all strategies. We conduct continuous verification and of course, increase the frequency of metering attention. But finally, we do continuous tracking of our meter performances because each equipment has a lifespan. So you continue to track the performance of each meter until when it gets to, apart from warning limit, if it gets to the red, I would say red line limit, they will recommend for replacement. And that is one. And then two, you equally track the performance of the meter in terms of efficiency, in terms of all the features it possesses comparatively to what exists in the technology around the globe. So wherever you identify each one after performance evaluation, then you have to recommend for replacement. It's all about continuous improvement in our metering strategies. Then we'll go to challenges. If you can go to the next slide. Okay, so challenges, like I said, I know many people have talked about this, operational criteria. If you have a new meter, if you have, just like as I mentioned, about 6 or different types of meters, it requires technical know-how, it requires knowledge, training, experience to be able to manage these metering facilities. So, and of course, you know, our personnel, oftentimes, some can leave, some new people are involved, there are intakes, so there will be continuous training of our operators, but that will come under solution. But operational criteria is one of the limitations we do encounter, because if consciously or subconsciously you just engage somebody who doesn't understand each meter and the principle of operation of that meter, it becomes an issue. Because there are other, like the uncertainty limit of a meter, an operator should have a basic knowledge of it. The turn down ratio, when your production is increasing, you should be able to know when to make a decision. When it is equally decreasing, you should be able to know the uncertainty bound so that you can adjust yourself appropriately. But without adequate knowledge, it becomes a challenge. And another one is obsolete fittings. Of course, like a meter that has operated for over, let's say 15 years, like PD meter or orifice plate meter, they are more of mechanical. And by the time you operate it with time, either it will be phased off or erosion effect will make the performance to reduce. So this is part of the factors we have identified as a challenge to our current metering. And of course, we have a solution for it. Then we have changes in measured fluid properties. If you're measuring oil, and along the line, the oil changes to water or gas passes through there, it becomes a challenge. We equally have process upset, and of course, fluid contamination. One or two of the speakers here have mentioned it. So these are the things we have encountered as part of our challenges, but they have a solution. Then another one is changes in process variables. Of course, changes in pressure, temperature, density, all the variables that we can use for correction of a metered volume is an issue, but then technology has made it easy. Instead of going to record it every minute or intervals of time, where you will not get accurate output at the end of the day, becomes an issue. Then we have effects of fluid dynamics. Some meters are not too good when the flow is not regular. If you have turbulence flow, it becomes an issue. If you have a kind of swell flow, it becomes an issue. But then these are all challenges to have in the process lines. But realizing all these challenges is good to know them. But then knowing them, you should have to come with solutions. Okay, so under solutions, we have to provide standard operating procedures or guides. Okay, I'll be rounding up. Standard operating procedures or guides, so that if you're an intake, if you're an operator, any meter, any facility you're operating, you must have a guide that way you'll be trained and then operate with. We probably have selecting meters with minimum uncertainties. Every meter has its own minimum, it has an uncertainty, and of course we know that no meter is 100% accurate, but if you select a meter with minimum uncertainty, you enjoy the benefit of it. In fact, all these factors, we deploy them so as to enjoy flexibility in operation, and we enjoy optimal benefit in the metering output, and of course, the benefit of sustainability. Okay, we still have laboratory and inline analysis. Okay, laboratory quality analysis. We use all these things to skim out operational issues. And then, of course, manage the process dynamics issues. Go to the next slide. Okay, so with a prudent metering strategy, we try as much as possible to reduce uncertainties in error with significant savings. But this goes a long way to say that there are metering modern technologies that can manage most of these challenges to advantage, or like metering data, process variables, flow turbulence, and fluid dynamics. And these are the technologies we're embracing. I will be glad if you have such a technology, you can approach us to work together to advantage. Thank you all.
Thank you. Thank you very much. So that's our last presentation for this section. Amin will be.
Sorry,
Mariam will
if I can just do a brief introduction.
Okay, go ahead.
The presentation.
Yes, so I was right.
Yeah, just a brief introduction. My name is Mariam Idrisu. I handle the flow measurement business in Emerson, Nigeria. We are a top manufacturing company when it comes to measurement products, control softwares, part of the Fortune 400 companies. We had a robust presentation planned for today with one of our experts for oil and gas measurements. Unfortunately, because of the delay during this program, he had a flight to catch and he couldn't, make it for the presentation. But basically, I'm just here in case there's any questions that you have about Emerson. I know some of you might be using Emerson products in your facilities. I handle the flow measurements. So basically your Coriolis, the mag meters, the vortex meters, the MPFM, the water cut meters. We also have density meters. Yeah, so those are basically the products I handle. Okay, so if you have any questions relating to that, and also to add that Emerson has moved away from mechanical types of meters, like turbine meters, what do you call it, venturi meters, senior orifice meters. We have moved away from that because now the world is changing. We're looking at more accurate meters that will give you less maintenance. You don't need to maintain it every single time. For turbine meters, you need to change spare parts, on a yearly basis. But for the meters that we're focusing on, they are not moving parts. They can last you for years, can last you for 20 years plus. So we're moving away from mechanical types of meters. I think that's an important note to add. And we have flow meters for different oil and gas applications, from the wellhead applications. I'm sure you're familiar with our ROXA MPFM meters, down to the separator lines. We use, you can use the Coriolis, can use our mag meters for the produced water. So we have solutions for the separator lines. We also advise that you don't use traditional types of mechanical meters for those separator lines because you can't guarantee 100% separation. In the oil leg, you can still have water present in there. In the gas leg, you can still have oil present in there. So you need to be able to measure the two-phase flow. Hence the reason why we're moving away from those traditional meters that don't give you those accurate flow measurements, to more modern flow meters. So if you have any questions relating to that, you can ask that. That's why I'm seated here. Thank you.
All right, thank you. So it's time for question. And I would like to start with a remark or a question. First of all, back in the days, we used to hear about the big data. The big data was all over the place. So we are now caught up in the course of trying to digitalize our oil field. So maybe Dami or Amin will need to respond to this. How does current innovation in artificial intelligence, visual reality, data analytics, fix into our EMP data acquisition, data validation, reconciliation, and allocation? Because that seems to be taking over where we are now. We need to catch up to know if those innovative ideas and technologies are going to be treated in silo, or there is going to be an integration between the AI, visual reality, data analytics, and data things, and the current worldview we are having now with respect to measurement and digitalization. Amin, if you're on the line, you want to take that?
Yeah, yes, by all means. Thank you for your question. In fact, this is a very timely question because
okay, thank
pretty
you so
much.
Yeah, I mean, everything about our digital transformation starts from the field to your smart control systems, because the topmost of the digital transformation is what we see as artificial intelligence, data analytics, and then not just that, predictive information output as well too, because you want to actually tell whether certain of your instrumentation or equipment is underperforming, or it's the health of that instrument is not going to be guaranteed, so that you'll be able to take very prompt action. And that is why in some facilities, they now commonize what we call smart valve positioners, because they want to control and check, because a lot of control valves are there in the field. And if you do not have understanding of when the valve will break down, you could be working and one day certain type of valve will just fail and then your process will just shut down. So, and these are the information that are in different silos because your control systems or your control cabinets operate different instrumentation at different locations. And so we have to pull this data, and that is the highest level of digitization we are talking about. So the digital transformation goes beyond even having the smart instrumentation. We are going to have smart or digital twin of the process, even our metering systems. We need to have digital twin because it enables you to next time when you want to design your metering infrastructure to be able to tell you the boundary limits and how you are going to optimize your design. Before we used to have, 3 by 33%, design of metering stations. Now we have a Z configuration, 2 by 100%. And that's because you have flow instrumentation that can take 100% of the capacity. And again, we are also talking about when you want to do meter proving, how do you understand that the line that the meter you want to line in series for test, that line is not passing? How do you understand? Because if it is passing, your meter proving will fail, or it will not, go to complete accuracy.
All right.
So these are the line of directions.
So thank you. We go to the audience. Any question from the audience? Yes.
Thank you very much. My question is very simple and to Emerson Process Systems. In the downstream gas subsector, we have, and I mean the very, very downstream. So when you have trucks delivering gas to the stations, we need meter to deliver such volumes. And again, the very down of the downstream will be for the delivery from those stations to the 6 kg, I'm talking about LPG in this case, and 12.5 kg. Do you have, in view of the very little volume required or mass required, do you have measurement solutions that will deliver rather than using those weighing of the LPG, whatever, cylinders? Do you have metering solutions to measure such little gas for end-use customers?
Sorry, what's the flow rates we're looking at here? What flow?
Typically,
you said very low.
I cannot speak to the flow rate, but I'm talking about 6 kg of gas cylinder, 12.5 kg, and then depending on if you are supposed to meter it, depending on the size of the small pipe you are using, but you just know what I'm talking about. Okay. Instead of weighing it on the weighing balance, which is typically what is done, we are talking about improving accuracy because the errors associated with the mass measurement. Do we have measurement solutions that you can deliver such little gas metered?
All right, so there'll be a pipeline, right? Is a pipeline? No pipe?
Currently, no. I don't know
pipeline. Because what we offer now, we can size meters from very low flow rates. Just give us the parameters, we can size at very low flow rates. For Coriolis meters, it has okay, you want to ask something else? Yes, you can use a Coriolis for gas application. You can use an ultrasonic for gas application.
No matter how little. No matter how little the delivery would be.
Yes, we have flow meters of 3/4 inch. We have really, really small flow meters. So we just need the process parameters, then we'll size the meter for you and you can install it. Yeah.
All right, Mr. Chairman, I guess perhaps, okay, Madam has a question.
Question I wanted to ask before is still there. Thank you very much for being here with us and for all the knowledge that we have learned today. Actually, I may be diversing a little, but I just want to find out. Yes, we are doing some production in country. Some quantity of products are being produced and is sold. At least it's going to help us in the forex. So how do you sell those products? Because at least you're going to take off shipment. Do you still sell the international rates, or is there any reduction in the prices, knowing that it's produced in-house, in-country, that kind of a thing, so that we will know that, yes, producing in-house can help us in one way or the other, because I know the refineries have not produced for a while. Thank you.
So which of the products?
Yeah, because you don't do okay, like the Aradel holdings,
Okay.
they don't do PMS. I'm just talking about even if it's the AGO, and the Cairo that they are producing, if you have to compare with the ones that are imported, where are we on that side of like pricing? Yes, Aradel.
Well, I think, or you want to take that question?
Although it's more of commercial question, but all the same, you cannot compare international price with local price. There's always an advantage of local price because we produce it here. You have your raw material here, you produce here. Yes. There's always a comparative advantage, cheaper. Thank you.
So the cheap is relative because 90% of the raw material you're using to do that is purchased outside the country and is dollarized, isn't it? Isn't it?
Not really dollarized because most of our vendors are local vendors, and most of our transactions too are in local currency.
Right.
Not everything dollarized.
Okay.
Not 90%.
All
maybe
right.
25%.
All right. Thank you. Any other questions before we call Dr. Femi for closing remarks? One more question and we'll be out from here the next couple of minutes. Thank you.
Thank you, everyone. My question goes to Damiete. He talked about, in metering, we have a saying that any instrument that is not or cannot be calibrated is worthless. So he talked about using a multi-phase gas meter to measure at the wellhead. So where and how do you calibrate the multi-phase gas meter? Thank you.
Okay, thank you. Thank you, sir. Basically, the one I talked about is Venturi, and that's a differential pressure instrument. So the sensitivity of the measurement is on the pressure transmitters and not on the Venturi. The Venturi is just, there's no moving part. So it doesn't really have to be calibrated. The only thing you need to calibrate intermittently is the pressure instrumentation, which might experience some drift over time. And that's basic standard plant instrumentation that everybody has and everybody knows how to do. Thank you. I hope that answers the question.
Come next year, more answer will come in.
Okay.
He has to keep the questions for the other 24 months.
So we are owing you answers, so come next year.
All right, Chairman, I guess that...
Are you asking if the calibration is being done locally or your question?
No. How do you do the calibration? So all...
And where do you do that?
And this is for multi-phase meters, right? There are different multi-phase meters. The one I talked about is wet gas meters, and relatively on Venturi technology technology. There are different ones. There are the ones that use gamma instrumentation, and over time, because of the energy absorption, the gamma energy will dwindle, and then you have to replace. But if you have to replace, you have to follow a lot of regulatory rules and requirements to be able to do that, because you don't want exposure. There is what we call dosing rates when you are close or operating around gamma instruments. So you have to also know when to leave that environment, when to approach and everything. So let's talk. Yes.
Yeah, it's having a very radiative source.
Yes.
Right. I think NUPRC have a very clear position on that. So I remember when Dr. Musa, we are revising the procedure guide over and over when he was in this system before he wanted to go and rest, even though he's not retired. So thank you.
Thank you very much.
Thank you very much.
Thank you very much, Dr. Ken. Please, can you kindly stand up so that we can have a group picture, and then I'm going to invite Dr. Olufemi Olaranju to please come forth to help us with the closing, then give us a total wrap-up on what perhaps we'll be expecting. Can we have the photographer? Are you in the house? Okay. All right. I will imagine it will be appropriate for the woman to, so that when they see the picture, they won't say that we had marginalized that with a multi-flow meter, so that her now is balanced. You can imagine whether it's gas or liquid, it's all balanced, what direction is going. Are we good? Please, can we have the chairman to join them? And of course, Dr. Sunday, please, can you come up quickly? Quickly. Is Dr. Sunday around, Council? If not, it looks like, all right, we need these images for reference purposes and to ensure that a lot of people who say they were here were actually here. So that this is part of the essence of making sure that we're doing measuring and evaluation. All right. Dr. Casio, it's not now to conclude business. Don't worry. We still have about 5 minutes to do that. Are we good? All right. Thank you very much, gentlemen. You can have your seats. Please, can we put our hands together for them as we invite Dr. Femi Olariwaju, Chief Strategist of Westpac Engineering, as he comes in to give us a closing. And then I will come back for a brief announcement, and then we can call it a day. Thank you, ladies and gentlemen. Over to you, sir.
Thank you very much, ladies and gentlemen. Thank you so much for taking the time. I like the question, the last question that was asked, the commercial question that was asked by the lady, because at the end of the day, what we hope we can actually evolve into as an entity is how these very big and strong, massive technologies can start to be applied to our day-to-day existence. Because at the end of the day, our core mission is to support the development trajectory in the way it affects the everyday citizens of the country. It's been quite an interesting 2 days. We've had the opportunity to look at multiple thrusts. Mostly we talked about technology, we talked about the people, we talked about processes. Things like equipment, local capacity development, transparency, traceability. You know, these are all key components of our technology that actually allows us very brilliant engineers to talk about what we do and how we do what we do. But you will all agree with me as we progress for the 21st century, there's no way we can talk about the value chain of activities in the oil and gas industry without clear considerations for environmental implications and stewardship. It's just here with us in the global context. It's here with us also in the local context. So earlier throughout today, even yesterday, we've been hearing things like net zero, energy transition, new energy. And basically what we are saying is that this global context, how do we define it and still align with the global requirements without suffering from equity and security perspective. So that is our mission. Those things will converge for sure. And that would drop, the word sustainability has also been, coming up. Sustainability used to be very difficult to define, but I don't think it's that difficult anymore. Because if you look at this group, for example, Sustainability, say for example, 440 million Nigerians by the year 2050. Our sustainability question is, how do we live a decent existence without harming the planet? That's the question we're asking. And we know that there is this product, hydrocarbon, that is a very massive source of cash flow for us, which unfortunately at this moment, we're all in agreement that we can do better in capturing them. So for those of us here that are in this particular line of work, I think we are quite privileged indeed, because our call to action is clear enough. How do we support the achievement of these very significant development requirements? And what role can our team play in it? And that is the essence of what we have been talking about today. So I use this opportunity to thank each and every one of you for taking the time for your patience. Tomorrow, we'll be looking at topics that include mid, downstream, and greenhouse gas emissions measurement. Ken had kind of hinted a little bit on that. We cannot get away from having those conversations, because they're going to have mid to long-term impact on what we do, including being able to even access funding from a whole lot of our projects, because we're going to be asked, so what are your plans on greenhouse gas emissions? We're talking about fiscal metering of natural gas and downstream measurements. Then greenhouse gas emission measurement, accounting, and management. And we hope that through the course of our conversations tomorrow, we'll start to be able to kind of mix these things up and depart knowing that, yes, from a technological perspective, we have clarity on what we can do with technology. But at the same time, how do we make sure that these narratives are framed such that we produce a result that answers the type of question that asks us, how can you use your technology to reduce the price of kerosene, like she's talking about? So at the end of the day, that is also part of our mission. So again, on behalf of our chairman, who is forever committed and consistent, I thank each and every one of you for taking the time. Please come tomorrow. We'll deliberately save the best for last. So I hope to see you again. Thank you so